Esta conferencia comenzará a grabarse.
Welcome to everybody, and we're glad to have here today Peter Associates and Geoff Beale, which is the chief advisor of the hydrogeology in many projects working with either underground mining and open pit projects. It's a pleasure to have you with us and sharing your knowledge, your activities. So, Geoff Beale, welcome to our institution, and we hope it will be one of the many future activities we may have, and to be sharing our passion for geology and what we need to be working on the mining activities. Thank you very much, Geoff. Go ahead, Eduardo, whenever you want.
Good afternoon, everyone. So I will present quickly who is Geoff, and to all of you has more information about his experience. So for those of you who are not familiar with Geoff, he's our chief advisor for hydrogeology globally. He has worked for 40 years in surface and groundwater control for the mineral industry, and he has worked in over 65 countries worldwide in all major industrial commodities and in all climatic zones. Geoff is most noted for his global knowledge of open pit and underground mine dewatering projects, and has been involved with many of the world's largest dewatering operations, and also has had significant involvement with a large open pit group. He has broad experience in the operational environmental aspects of leach pads, waste rock facilities, and tailing systems, and has played a lead role in the design of and monitoring of closure programs for several mine sites. In recent years, he has studied the role of water in geotechnical engineering, gathering data and experience from many sites worldwide, and also co-edited, along with John Reed, the recently published CSI RO guidelines for evaluating water and pit slope stability, and has contributed chapters to the guidelines for open pit slope design, and also the guidelines for open pit slope design in weak rocks, and the guidelines for mine, waste dam, and stockpiles design, coincidentally co-edited by our CEO, Mark Hawley. So that's a very quick introduction to Geoff. So now begin a very good, interesting presentation in the open pit dewatering. So Geoff, if you can share your presentation and go ahead.
Okay, thank you, Eduardo, and thank you, Carlos. I will shut down my camera while I do the presentation. And it will take about 1 hour to do, and so I'll go quite quickly because there's quite a lot of material, and then we'll have time for some questions at the end. So I hope you can all see that. So I've divided the presentation into 9 topics. Firstly, how water affects mining. Secondly, principles of mine water control. Thirdly, dewatering methods. Fourthly, one slide on passive water control. Fifth, the difference between dewatering, general dewatering, and slope depressurization. Then I'm going to talk a little bit about surface water, which is very important for mining. How to predict dewatering rates, a couple of slides on numerical models, and then finish off with monitoring and reconciliation. But first, we're going to talk about how water affects mining. Why do we have to think about water? So there's a number of aspects, but these are the 2 most common ones. These are the 2 most important ones. Firstly, operational. If we don't get rid of the water, we're not going to get access to mine. And that comes with a whole heap of associated costs, explosives, more equipment wear, trafficability, haulage costs, and safety. So I'll talk about that in the next slides, but the operational aspect is clearly important. But the other aspect, which is not so much on people's radar screen so much, is the slope stability. But the slope stability is actually the biggest factor in terms of cost. So any water in the slope has a negative effect on stability. And for a large mine, for instance, a large porphyry copper mine, if we can cut the slopes a degree steeper throughout the entire pit, we can save up to $500 million in stripping. And the only thing that is changeable, the only geotechnical parameter that's changeable is the water pressure. So those are the two aspects. Just to talk a little bit about operating costs. So I won't go through this in detail, but the key ones are safety, drilling, so drilling blast holes, sampling, if we have water in blast holes and water in grade control holes, we get biased samples and we don't get as good an ore control. Blasting, we've done quite a bit of work. The incremental cost of a large blast hole between the use of emulsion or ANFO can be up to $300 per hole. Loading costs are higher if they're wet. Haulage, you've got the equipment wear and the tire life reduces by about 15%, and crusher throughput is also reduced typically if there's too much water. And then the obvious one is the mineability and the stability. So a lot of operational cost issues associated with water. So there's a number of mines I work at where they have difficulty depressurizing or dewatering the pit floor. If you mine into the water table without doing your advanced dewatering, you can have you get into a point where you can't load the blast holes and you can't advance the pit floor downwards. This is an example we did recently that we were able to dewater it. So this is a floor of a major copper pit. So we defined where the structures were. We put pilot test holes on the structures, and we did some. In this particular case 7 test holes, and we found that these are relatively short holes. They were 50-meter holes, but we found where we drilled them on the structures, we were getting good flows, and where we drilled them away from the structures, we weren't. So we went ahead and put temporary wells along the structure. We dropped the water level 30-40 meters below the pit floor, and they were able to advance the pit floor downwards and achieve their mine plan. So that's an example where we were able to put wells in the bottom of the pit and achieve dewatering as a short-term measure. So in terms of slope stability, what does water do in terms of slope stability? Well, I'd like to divide it into 2 factors. Firstly, water changes the resistive force of the material. So if we have water present, the resistance of that material to shear is less if we have water. But the second, which is often forgotten about, is water also increases the driving forces. So if we have water behind a structure, it can increase the driving force on that structure. It can reduce the stability of the slope. So there's several other lesser concerns, volumetric changes, for instance, consolidation in weak materials. But the resistive forces and the driving forces are the 2 key issues for water in slope stability. And I'm going to talk about each one of those in terms. So the most important concept is the effective stress concept, which essentially changes the resistive forces of the material. It's a relatively simple concept if you stand back and think about it. It's sometimes made to be more complicated than it is. But if you think about any horizontal plane, the forces on that plane are the downward weight of the material, which is trying to compress the plane, and the upward force of the water is trying to push that plane apart. So clearly, if you can reduce the upward force of the water, your net effect of the downward weight of the material, the downward stress, is greater. So by reducing the water pressure, you reduce the pressure on the failure surface, you increase its shear resistance. And I like to think about it, if you have two plates of glass, if you have no water between those two plates of glass and you try to slide them, then it's difficult for them to slide because of the frictional resistance of those plates of glass. If you put a small amount of water between them, they will slide very easily. And the more you press on those pieces of glass, the more they will slide. So the more you press, the more the effect of the water pressure, the less the shear resistance. So essentially, by reducing the pressure of that shear plane, you increase its frictional resistance, you increase its stability. And of course, most situations we get into aren't flat, they're angled because of the slope. So here's an example of the same thing on a block. So as you reduce the water pressure on this block, you increase the frictional resistance, you increase the stability, and you reduce the likelihood of that block sliding. So again, just think about it as if there's water pressure on the surface, the block becomes more buoyant, it becomes easier to slide, less friction. If you remove the water, there's more friction and the block has less tendency to slide. And this is the same thing with slope. This is an illustration from the book that Eduardo referenced. Again, this is a failure surface. If you reduce the water pressure from here to here, essentially you don't change any other forces, but you increase the resistive pressure. So if you reduce the water pressure from there to there, you increase the resistive force from here to here. So you get more frictional resistance and less potential for sliding. And when we think that the only thing we can do, we can't change the geology, we can't change the geomechanical properties, but we can change the water pressure. So the water pressure is the only geomechanical parameter that we can change, and so it is the only thing that we can control in the slope. So that's the effective stress concept, which is the resistive forces. I hope that's clear. I'm going to just now give you an illustration of the driving forces. Now, driving forces are often ignored in the analysis. They're not. They have to be specifically added to most geomechanical programs. That's something we're kind of working through with a large open pit group at the moment. But a couple of examples here. This is a fault which dips into the wall. You can see what's happened here. This is a real example, and you can see this large multi-bench stability. And if you look closely, you can see the fault plane behind the instability. What's happened there partly is we've reduced the pressure in front of that structure, but we haven't drilled holes through it to reduce the pressure behind it. And so this water pressure exerts a force on that structure. It tries to push it out, and it reduces the stability. Here's an example of what we call toppling failure. So in this case, the structure is dipping slightly into the wall. In this example, it's almost vertical. What's happened in this example is surface water has got into the dilated cracks associated with this structure. And again, the water pressure reduces in front of the structure. The water within the structure and behind it stays high. So the force of the water tries to push the structure and increase its tendency to topple. So those are a couple of examples where the force of the water actually reduces the stability. And another one is what we call piping. So this is an open pit coal mine. These are sand layers. So you can see there's a sand layer here and a sand layer here. And so as we expose the slope, this sand layer has got water pressure in it, and the water pressure pushes the sand out and causes what we call piping. So you can see here the piping, the sand is all pushed out because of the water pressure. You can see these two lines here, and so it weakens the surface. It reduces the ability to support the material above it, and this photograph doesn't show it, but the rest of this slope here had failed, and this particular slope had failed once it had been exposed. So the water pushes the sand out, and the material above the sand collapses, and the slope fails. So those are three examples of driving forces. So that's really in a very quick 5 minutes the effect of water on slope stability. But think about it as resistive forces, effective stress, and driving forces. So in terms of dollars, so typically we've looked at this a lot over the years, and if you get rid of the water from a pit slope as a global average, of course this is hugely variable, but as a global average, for every dollar you spend getting the water out of a pit, you'll get a $5 payback in terms of improved slope angle or improved pit performance. This is a little graph I did with some real cost analysis. I did this a few years ago, but it just shows this is the cost of the pore pressure control, and this was the dollar saving in terms of stripping. So you can see, for instance, here we spend 40 million and we get close to a 4-to-1 payback. In that particular case, we get a $200 million payback in terms of improved slope performance. And this is from the slope design book, so you can see if we can steepen up the slope, it's less material we have to strip at the top, it's more ore we can get at the bottom. So the importance of water in slope design cannot be overemphasized. So we're going to just talk about just some principles of mine water control. What are we trying to do? So just divide this into open pit and underground. So for most open pits, the goal is to lower the water table to below the pit floor or close to the pit floor to enable access and to enable the slopes to depressurize. And so we have to remove the groundwater inflow, divert surface water, remove rainfall, and manage waters in the pit slopes. But in an open pit, our goal is to lower the water table to allow access for mining. In underground, often we're able to work below the water table. Now, that's not totally true. Many underground operations have to lower the water table, but when we look at an underground mine, the first thing we look at is, can we work this operation without having to lower the water table? And there's a fundamental decision when you look at an underground mine, is whether you try to encourage the inflow and dewater it, or whether you try to exclude the inflow and not dewater it and not have to manage the water. If you encourage the inflow, if you allow the water to come in, it reduces the water table, it reduces the water pressures, and enables you to mine typically with less risk. But you have to manage and pump the water. If you exclude the inflow, for example, by grouting, then what it means is that you don't lower the water level, so you're mining under higher pressures. So you have more potential geotechnical concerns because the rock above you is under higher pressure. But the advantage is that you don't have to manage the water. So it's a fundamental decision whether to encourage or exclude the inflows when you're looking at an underground project. And the third I put in as a classification is underground development, because, for instance, if you have an ore body which is 500 meters deep, it may take you 2 years to access that by either a decline or a shaft. It probably takes you a couple of years to get access, but you have to dewater and manage water in that access from the start, because you're obviously going from the ground. And so even if you have an underground operation that you can mine without much water, you've still got to deal with the water in the development as it goes down from the surface. So just going to show this in an example. So this is an underground mine in Australia that I've worked at for a long time. So the ore body is down here. This is in a breccia. It's very, very tight rock. So they've been mining this ore body for 30 or 40 years. The inflow rate is about 5 litres a second. It's a large mine, but it produces relatively little water because it's in this green, tight rock. They're looking to do a large expansion with an open pit. As soon as they go with an open pit, for instance, here, they have to now think about mining all through this sedimentary sequence, which is above the ore body. So this sedimentary sequence in this case has got quartzite, sandstones, shales, limestones, permeable materials. They don't have to worry about that if they're underground, but as soon as they put a pit slope through that material, they have to implement a major dewatering program. So that's the difference between mining underground, where they're away from the water, they're below all the water, they don't have to worry about it. But as soon as you cut the pit slope, you expose all those materials, you have to dewater. So when do we get lots of water in a mine? So these are probably the largest hard rock dewatering programs in the world today. There's a couple of others which probably fall into that. But when you look at this list of the top 10 dewatering projects, the thing that you see more than anything else is that 7 out of 10 of those operations are in limestones or carbonates. So Goldstrike, Concola, Pontani, Frontier, Cortez, Katanga, Nika, and Grasberg are all in limestone or dolomite rocks. So the carbonate setting, the limestone setting, is conducive to high dewatering flows, and particularly in southern Africa, for instance, where you have lots of rainfall as well. So most large dewatering projects occur in 4 typical settings, not all of them, but the majority. So for instance, in Nevada, we have ore bodies which are located adjacent to big basin fill alluvial valleys. So many of those ore bodies, they have to pump a lot of water from the alluvium to get to the ore body, either underneath the alluvium or laterally to the side of the alluvium. So large alluvial basins give you high dewatering rates, and some of those Nevada operations are also in carbonates. Southern Africa is another domain with very high dewatering flows, dolomites with active recharge. So that's the second category, which is going to give you large dewatering flows. Thirdly, and this is a lot of these are coal operations rather than hard rock, but the sedimentary basins in Europe, in Poland, in Germany, and in Eastern Europe, for instance, will all give you large dewatering flows. The largest dewatering project anywhere is the Garschweiler lignite pit in Germany. And the fourth is in the Pilbara, where many of the iron ore mines in the Pilbara are now having a connection to dolomite or to other carbonate features, and are also starting to become very large dewatering operations. So you can categorize the large hard rock dewatering programs into 4 different categories, which are typical settings where you're going to get large dewatering projects. So just to look at some dewatering options. So one of the things we always look at is in where you have a weathered material, or in the tropics where you have a saprolite. So you get, typically what you get is a decoupled groundwater system. So when you mine this, the rock will dewater, the weathered material above it will often stay saturated. And here's the example. This is the same example. So you get decoupling of the water level in the bedrock and the weathered material above it. And this is a typical West African or Central American saprolite. So in this particular case, on all these, you have to pump your dewatering system is in the fractured rock below the weathered material. So you're targeting fractures below the weathered zone. And then you, in terms of depressurizing, so that gives you your general dewatering. And then you have to then monitor the water pressures in the weathered material or the saprolite above that to make sure that you get enough depressurization to keep the upper slopes stable. So anytime you have a weathered material or in a case of a porphyry, a leach material, you'll get a decoupling of the water levels. The water level in the bedrock will drop, but the water level in the upper weathered materials will stay in place, will decouple, and typically won't drain without artificial or improved depressurization. Another example, which is the Grasberg mine in Indonesia, which is on a very unusual case. So you can see this is a picture of the pit. It's a 1,000-meter deep pit. They've pretty much stopped mining in the pit now. But you can see it is in a sedimentary syncline. So the ore body is down here. It's in a sedimentary syncline. It's in very, very caustic carbonate rock. And what they did, what they had the foresight to do in the early days is drive a drainage tunnel in below the pit. And that drainage tunnel dewatered everything above it, because it's in a syncline. All the water level in the limestone, all the water pressures dropped. They drill drain holes from that tunnel to increase the capture, but essentially the tunnel dewaters the entire pit. And that tunnel, they had the foresight to put in that tunnel at the start, and that tunnel has enabled them to mine the entire Grasberg pit without having to do any dewatering. They have to do depressurization of the slopes, and they have to manage surface water in the bottom of the pit. But in terms of dewatering, the tunnel has taken care of all their dewatering. And it's so permeable at Grasberg that when they get rainfall, and they've done a lot of tracer tests, when they get rainfall on the surface, that water can get into the tunnel sometimes in less than 24 hours. So hugely permeable, hugely interconnected limestones. So they're going to talk about dewatering methods. So there's only so much you can do. Pumping wells or pumping bores, either interceptor, where you're trying to stop the water getting to the mine. Peripheral, where you're putting wells on the pit crest or in the upper parts of the pit. Or in pit, where you're getting maximum effect, but those wells are in the way of mining. Horizontal, vertical drain holes. Drainage tunnels. Those are the three active methods that you can dewater. So none of this is particularly rocket science. It's not, they've all got variations, but those are the three main methods. There are passive methods. I'll give you a couple of examples of that: slurry walls, grout curtains, and so on. And in-pit sumps. And what we're seeing more and more importantly in terms of slope stability is surface water control. We're seeing that we've come to the realization that many of the instabilities that we see can be correlated to surface water. In fact, there's been some recent research done to show that over half of the global instabilities, or the instabilities that are in a global database, can be correlated with either rainfall or surface water. So these are the methods. This is the ones we normally use. So wells or bores, drains or tunnels, and I'll go through each of those in turn. So this is an example. This is a project I did 30, 40 years ago in Nevada. So this is a kind of classical dewatering of an open pit. So most of the water is up in these alluvial sediments to the west, and so we pumped probably 80 to 85% of the water from shallow wells. The wells were about 120, 130 meters deep, located outside the pit, and the goal was to stop the water getting towards the mine. So the advantage of this is we got the water clean, it didn't go through the mineralized zone, and we were able to prevent water from recharging the bedrock, or greatly reduce the amount of water to recharge the bedrock. So for this particular case, we had a line of 40 wells, about 130, 140 meters deep, which took care of about 80 to 85% of the water. We had then deeper peripheral wells to try and get the residual water from out of fractures. And then we had wells to the north and south of the pit, or in-pit wells, to deal with the residual water beneath the pit floor. So these other two produce less than 10% of the dewatering rate. So this is a different mine, but the same concept. This was another mine in Nevada. So again, we've got same concept. You can see this is the base of the alluvium here, and then we have the rock underneath. So we have a line of high yield alluvial interceptor wells outside the pit. We try and get the water before it reaches the slopes. You can see these slopes are dry. The water table in this case is about the level of where my cursor is, but the wells have got everything dewatered below that. In this case, we also have a line of shallow wells, alluvial wells inside the pit, just to make sure there's no water getting into the slopes here. And then in-pit wells are done from convenient benches inside the pit. And one thing we have to, if we're putting in these in-pit wells, we have to make sure we design access into the mine plan. So mine planning is an important function for any dewatering system. An example of an in-pit well, this is quite an old photo from the Escondida mine in Chile. So you can see where we put the well in a convenient location. In this particular case, we've got a ramp, a permanent ramp, which came down. So we had this access bench created, and so this well operated for several years before this particular pushback. So we tried to put the wells between the ramp and catch benches. So we can artificially widen the ramp here, as we've done in this particular case, to give ourselves access to drill the wells. One thing that we must note with dewatering wells is well losses. I won't go through this in detail, but essentially, this is the pumping water level in the well down here. But the aquifer outside the well, the water level is up here. So there's four components of drawdown. The first is the true aquifer drawdown. That's the only thing that's important for dewatering, is this true aquifer drawdown. But we have then what we call well inefficiency, or our well losses, which is the local friction losses as the water goes through the fractures close to the well, and the velocities, the water velocities gets higher and higher. So we get friction losses here. We get losses as the water goes through the casing in the screen and gravel pack, if we use gravel pack. So that's the third component. And we get turbulent losses inside the well itself. So there's four components of drawdown. The only one of value is the true aquifer drawdown. And so it's very important to minimize these local well losses in dewatering wells, because this is just wasted energy and wasted drilling. So another thing we have to think about when we're dewatering is the depth at which we encounter the water. I'll give you this example. These are two identical wells, and this is a fracture zone, which an identical fracture zone which dips. And this first well hits the fracture zone at 100 meters depth. This second well hits the fracture zone at 200 meters depth. So we start off with a water table initially, and the wells are quite good. They're good performers. but we can put 100 meters of drawdown on the fracture zone here, but this well we can put 200 meters of drawdown on that fracture zone. So this well is inherently better from the start because it hits fractures deeper. Now, less than 2 years later, we've dewatered the ore and the water table has dropped to 50 meters. So for this particular well, we've halved the drawdown that we can put on that fracture. So essentially we've halved the yield of the well. But this one, where we hit the fracture deeper, we've only reduced the head on this on the fracture by 25%, by a quarter. So the performance of this well is only reduced by 25%, where the performance of this one is reduced by 50%. And then we think, again, 2 years more into the future, where we've got the water level now to 100 meters, this well is dry, it's finished, it's dewatered the fracture. However, this one is still got plenty of operational life because you hit the fracture another 100 meters below the current water table. So it's very important when we're dewatering to hit our fracture zones or our target zones as deep as possible below the pit floor. The other thing is pilot holes. The variability in fractured rock is always inherent. So you can hit fractures in one hole, you can move 10 meters in many formations or 20 meters and hit dry rock. So it's very important to do these test holes before we spend a lot of money doing production wells. So for instance, if we drill a pilot hole and we measure the airlift, this particular case is ideal. So this is our static water. We didn't get much flow here, but here, right at the base of the hole, we can hear an obvious good inflow zone associated with a fracture here in red. So we know, for instance, straight away, we've hit a fracture, we've hit it deep. We know that this is a good site for a production well. We know we're going to invest the money to put in a production well at this location. So very important to test the ground before, with small diameter, low cost holes, before we invest the money into production wells. Another thing when you're designing dewatering wells is a lot of times they're going to be blasted around. So the input wells, mines now have got very good at blasting around wells. So this particular blast that you see in the photograph here has got two $1 million wells inside the blast. There's one here and one there. And what they've done is they've cut the blast, as you can see here, to give them free faces so that the energy can dissipate outwards, so that they release energy to the free faces. And they sequence the blast from here. You can see this is the start of the blast. They've just let the blast, but the blast will go slowly across here to dissipate the energy and to minimize the damage, minimize the vibration on those two production wells. So many mines now have got good procedures for mining around wells. So this is another situation where you get into. This is a mine in Peru where they had a major failure of one of their slopes. This was the failure, the shear zone, and so we had to depressurize the rock underneath the shear zone. So in this particular geometry, we had no option but to drill the wells through this shear zone, and considering that this shear zone is moving. So we had to drill, in this particular case, 5 production wells through the shear zone. And what we found is, provided we kept the flows constant in those wells, the local change in effective stress minimized the shearing. So we were able to operate these 5 wells, depressurize the contact zone, reduce the stability for long enough for them to be able to mine the pushback. And you can see after it was done, we video cameraed the well, so you can see the shear. In fact, as soon as we shut these wells down, they all sheared, and we lost them all. But they were in place long enough to allow us to mine the slope. There's 5 or 6 mines now, 6 in total that have done directional drilling to get better geometry. So this is an example in Arizona where this is the pit, and rather than put in wells here, they've drilled underneath it. It all sounds very easy, but it's expensive. One of the things that people forget is when you're directional drilling, when you're using a motor or when you're using a standard motor, you're steering, you can't put all the weight on the bit because you're steering. And if you're in a hard rock, that's fine if you're oil drilling in a softer sediment or a shale. But if you're in a hard rock and you can't put the weight on the bit, it makes the drilling very long and very expensive. So there's a number of mines that have done this now, but it's not as straight. It would seem very easy and very straightforward to think about putting a directional well like that, but there are a lot of problems that go with it. And you can see even on this one, what we did when we drilled it was we achieved the turn here, but we got to this point and then we decided to drill straight and stop steering it purely to increase the penetration rate and to reduce the cost of drilling. So it's a great idea, and I think more mines will do it in the future, but there are some major considerations in terms of the cost, and mines that have done this have typically paid $10 million or more for the wells. Just going to have one slide on passive water control, which is something that's done a lot in underground, but less so in open pit because we're dealing with big surface areas. But this is an example from a coal mine that I worked on, and you can see here what there's a river here. It's out of picture. There's a major river. The pit is on over to the right out of picture. And so we've got the pit here. We've got a river over here. We've got about 30 meters of sand and gravel. And so we excavated a slurry wall. You can see there's a long boom excavator. This slurry wall is actually 29 meters deep. Fill it with bentonite slurry, and it was about 3 kilometers long, and it reduced the flow in the sand and gravel by about 90%. So in the right application, in a sedimentary setting like this, it paid for itself. There's a few mines that have done this. It's quite common in the coal industry. The two pitfalls are always at the bedrock surface, not always, but often at the bedrock surface you get a shattered zone. So it's very difficult to key that slurry wall because we're doing it with an excavator, very difficult to key the slurry wall. So there's always potential to get a lot of loss in the broken zone, in the fracture zone at the bedrock surface. And the other thing is if we keep our heads high on the outside, it also increases the driving pressures to force water into the bedrock. So this is a good thing to do if you have the geometry, but again, trying to key it into rock can be difficult. So it's not something that's common in hard rock mining. It's more common in the coal industry, but it is definitely an option, and it's something we're currently looking at a couple of our projects. So just going to talk about the difference now between dewatering and depressurization. So the two go hand in hand, but they are uniquely different. So just the 4 pictures here, and in each case, the right-hand side of the picture is nicely dewatered. It's a homogeneous rock. It's nicely dewatered, you can see. And so they don't need any depressurization in that particular side of the pit. But there's typically three situations where you need to locally enhance the depressurization. First, when you get these in-dipping structures, when you get structural compartments. So most structures will act as barriers across their strike. So when you pump from this side of the pit doesn't drain. And so you get pressures behind these structures, and you've got to go in there with horizontal drains to alleviate it. Second is when you get an argillite, clay, low permeability material, shale in the wall. And sometimes you can dewater underneath that but leave the water pressure hanging in the weaker, softer materials. So again, you've got to go in and alleviate that, often typically with vertical drain. So again, a soft material, a weaker material, lower permeability material will decouple from the main dewatering system. And the third is where you have a bedding or a paleosol or a flatline structure, which causes the water to hang up above the structure, so the structure won't drain because it's the horizontal barrier, even though, again, in this case, that you can dewater underneath it. So again, you have to go and deal with this water locally in the pit to improve the slope performance. So 3 situations: 1, structural barrier; 2, low permeability material; and 3, bedding or sub-horizontal control. And you can get in a situation where even if you're above the water table, if you've got a wet climate, you can have poor pressures in the slopes and clays, even if you're above the water table, or in often cases if you're next to a river, or what you see in many mine sites, if you have leaky tanks or leaky pipelines or other leaky facilities that will cause water pressure to enter the slopes. And in Chile, for instance, many of the mines and many of the slope stability issues we have to deal with are because of leaking facilities, leaking tanks or leaking pipes or other facilities which leak water into the slope. So each case, the dewatering system works on one side of the pit, but they require depressurization, local depressurization on the other side of the pit. And the most common form of depressurization is horizontal drains. A few examples here. This is an old photograph from Escondida. This is a very small drill that they used in Peru, and these are also very small adapted underground work drills in British Columbia. This particular site operates 3 horizontal drills all the time. It's probably the largest or the most advanced site anywhere in the world for horizontal drains. They do their entire 2 very large pits, and they do their entire dewatering and slope depressurization with horizontal drains because they've got subvertical structures. And so most pits or most large pits now will operate horizontal drains in terms of improving their slope performance. And the horizontal drains itself is a science. Rather than just shotgunning and drilling anywhere, it's important to think about what you're doing. This is a real world example from a mine in the US where we had a very weak monzonite here, but we had limestones behind it. And if we'd have just drilled these short drains into the monzonite, the surface area on the contact here would have just kept feeding water into the monzonite, and the recharge would have always been too high for the horizontal drains to depressurize the slope. So what we had to do here is drill some longer drains into the limestones to targeting fracture zones, so we could dewater the limestones to allow the short drains in the monzonite to be more effective. So we have definite targets for the drains, and when people ask me the most important thing about horizontal drain drilling, it's to really define a target and to define the geology so you can think about what you're trying to aim for with your horizontal drains. Again, a large pit seek that has to drill horizontal drains on most of their walls, and you can see here this is the horizontal drill, and you can see how they've sequenced it with the mining operation. So it's important for mine planning and mine operations to be able to plan for the dewatering system, and in this particular case, the horizontal drain drill. So another application is vertical drains, which we use quite commonly. Again, this is a permeable rock which is dewatered, but we have this paleosol. In this particular case, it could be weathering up the bedrock surface, it could be a stratigraphic layer, where we have to go in, put in these vertical drains, allow this water to drain downwards into the main dewatering system. So again, it's a common application vertical drains where we're trying to just alleviate water that's perched and bring it down into the main dewatering system. One advantage of underground tunnels is that the efficiency of the drain holes is much higher. So when we're drilling, if you look on the right hand side here, when we're drilling from a pit, we may start off with this light blue water table, and so we're drilling, you know, a third of the drain hole is dry, and so therefore is wasted. And then when we finish the drain holes, the water can be close to the end of the drain. So the hydraulic contact of that drain hole is very small because much of that drain hole is drilled through dry material. When we drill from underground, or if we have one of the big advantages of a drain gallery, is that the hydraulic contact is much better. The drains are more efficient because now we're drilling from below the water table. So a much greater part of our drain is saturated. We have much better hydraulic contact with the formation. So the drains are much more efficient, and the flows are much more sustained. So many of the times the reason for doing a drainage tunnel is to give ourselves access to drill drainage holes to improve the hydraulic contact to give us a more efficient system. So a couple of examples of large pits with drainage galleries. This is one in the United States where you can see the portals here, and they've tunneled in both directions beneath the floor, and you can see the horizontal drains. And the goal in this particular case has been to pressurize the lower part of the pit, the lower part of the wall. You can see we've drilled fan drains on this one. And typically everything put in with relatively small underground drilling equipment. This is another complex tunnel. You can see this one has got probably 400 drain holes from it, and you can see it's quite a sophisticated engineering system to reticulate all the flows and to get the water out of the underground and into the pit dewatering system. So talking a little bit about surface water control, it's something that's been on my radar screen for a long time now. Surface water is one of the most important things for open pit mining and slope stability. So most of the instability that we see around the world is quite shallow. It occurs within 50, maybe 70, 75 meters to the slope. So most of the instability occurs where the rock is weathered, where it's blast damaged, where it's deformed because of mining. And as I said earlier, over 50% of global instability can be correlated with either precipitation or surface water. So surface water is a major role for open pit mining and instability. And this is a typical failure. This is quite a large failure. It's a big pit, so it doesn't look particularly large, but this is just a skin failure. It's about, this one's about 60 meters deep, and it is caused by, this particular one is caused by a leaky pipeline. So we've got a leaky pipeline. It puts the surface water into the slope, causes the instability. So surface water is a major factor for open pit mining. And this is a very, very common application. So we see many pits with this. So we have a weathered zone up here where most of the, where we have very, very low permeability compartmentalized rock, very, very low groundwater movement. So most of the flow we get is through the weathered material, or if there's some alluvium here. The path of least resistance, the path that most water takes, isn't through the water table, it's down the blast damage zone. So again, we have a situation where most of the flow in large hard rock mines comes down the blast damage or the deform zone. And so if we get that water then comes into a fracture that's dilated, it can give us big water pressures in that fracture and can lead to instability. So this shallow near surface water is something that the mining industry is becoming increasingly aware that is the real problem rather than the deeper groundwater. So it's very important we retain that focus for our piezometers and for our modeling. So again, this is a example of good surface water control on the ramp. You can see they've got, this is a mine in a tropical environment. You can see they've graded the ramp, so all the water runs along the inside of it. They can clean the ditch with a grader, so they don't have to deal with excavators. They can just come along with the grader and clean it. And you can see again the same similar thing here. So the water comes down the inside of the ramp. You can see it comes down this side. So it's away from dilated joints and cracks associated with the crest, and the drainage comes down neatly down the inside of the ramp, and that's good surface water control. So ramps are very, very important, and getting the right engineering on ramps is very important for surface water control and surface water management. So there's only a couple of slides, but surface water is very important. And not only where in wet climates, but also in dry climates where you have maybe occasional storm events, and those storm events can give you instability. So just a couple of slides now on prediction of dewatering rates, or just one slide. So the best way I think to predict a dewatering rate is to use a water balance approach. So if you know the geology, you can figure out the recharge and the storage of each of the geological units. So you know the drainable storage, you can figure out the recharge, you can figure out the way they interact, you can sum up the different geological units and obtain the mine dewatering rate. So that is, to me, still the best way to estimate the dewatering rate, is to look at a water balance and to add up the different geological units and make and come up with an overall dewatering rate. We can use analytical equations where we often simulate the pit as a large diameter well or void, and so those are also good first pass estimates, provided we know the assumptions. We all want to jump in to do numerical models. So I have a slide on numerical models. They're fine, provided they're constrained and provided we think about the assumptions. So the models are always constrained by the broad geology, the broad assumptions, rather than the local details. So if we do a numerical model, it's important that we think about what that model is constrained by and how reliable the results are. So the most important thing with any of this is the geology. If we understand the geology, we have a better estimate of the dewatering rate. If we don't understand the geology, none of these methods are going to work. So the more empirical data we can get from pumping trials, the better. And we also think we're not in a large dewatering program where you may have drawdown going several kilometers from the pit. It's impossible to fully characterize that area of drawdown. So again, you're always going to be relying on assumptions. And there's plenty of mines around the world, and the chances are that most of them, that somewhere in the world, somebody will have done something similar. So benchmarking with other sites is an essential part of the process. So a couple of slides on numerical models. Everybody thinks I'm anti-modeling. In fact, I'm not, but I just would like to see more focus placed on how we apply and how we use numerical models. So if we think about our models, it's not realistic to have a large site scale dewatering project where, or a dewatering model where we have typically high grid size. It's not realistic to expect that model to be able to simulate details around the pit slope. So I think we've got to think more about what we're trying to do with our models, look at the scale, look at the complexity, and apply our models to the questions we're trying to answer. And many mine sites, it's not at all a simple one model typically will not address all the issues. So several mine sites may end up with several different models to address specific issues. So there's no such thing as a one model fits all approach. People often ask me what's better, mod flow, feed flow, or any of the common codes. My answer invariably is it doesn't really matter. So what matters is understanding the site and understanding the geology. The assumptions you put into the model are much more important than the type of code that you use. So geologically, the geological uncertainty and the uncertainty in the setting is tenfold more important than the type of code that you use. So it's where most of the uncertainty we get in our predictions are because of either broad scale or even local scale geological uncertainty. So that's normally the biggest source of error in our model. So the other thing I say to people is, if you know what the answer roughly should be before you start the model, you have a better chance of focusing the model. You have the better chance of having a successful model. But always think about the geological uncertainty, which is the biggest source of error in any numerical analysis. So I'm nearly done with my hour, so I'll go a little quicker. We've just got a few slides left. So this is an example of a misapplication of a model. So this particular mine site, they simulated a model. This was the water table here, and they put that into a geotechnical analysis, and there was no effect on the stability. But you look around the pit, and there was a lot of instability in this pit. And again, the instability was caused by all this shallow water coming out, in this particular case, the alluvium, not from the main groundwater. So the model had been misapplied. So the focus on the model was the deeper groundwater, which was not important. The real importance was the shallow groundwater in the zone that had been disturbed by blasting and mining. So in this particular case, they'd done a model, but the model had actually misled them and caused them to get the wrong interpretation in the geotechnical analysis. So modeling is a process. Start off with the conceptual, as I say, the goals. The modeling itself is only a small part of the process. Thinking about the results and applying those results are just as important as doing the model itself. So finally, just to talk about monitoring, a couple of slides. So once we've done all our studies and we get going, it's important then that we monitor the performance, monitor the water levels, monitor the bore pressure, monitor the pumping rates, so that we can feed that information back into our analysis and improve our understanding. So mining is an ongoing circle between designing the system, implementing the system and monitoring it, using the data from the monitoring to verify and validate our system, and then feeding that back into the design. So it's this cycle of implementation, of design, implementation, verification, feedback into the design. And so it's a cycle that always improves our understanding of the system at any mine site. And set targets. So if we have a dewatering program, it's important to think what we're trying to achieve with it. So in this particular case, this is date down the bottom, and this is groundwater level on the y-axis. So in this particular case, we were trying to dewater a pit to achieve slope stability. So we used our geotechnical analysis. So these are the piezometers, and so this was our forward projection. And so we used the geotechnical analysis to say if we could get our piezometers into the green zone, that pit would have a higher stability, a factor of safety of greater than 1.3. If our piezometers were in the orange zone, we'd have marginal stability. So we would try and take steps to improve the rate of drawdown. And if we got into the red zone, we were looking at potentially unstable conditions. So what we're trying to do is use the monitoring data to set ourselves targets. In this particular case, we wanted to be below the forward projected line. And so we were able to then design the system and operate the system to achieve the targets, which provided accountability for the program and enable the management to know when they were spending money and how they were spending it. So finally, monitoring. This is the last slide. We've got good geotechnical tools now to be able to monitor the result of the drainage. This is an old slide now. I've used it. It's a good example. So this was a slope in a mine in New Mexico in the US, where this particular slope was unstable. This is the radar plot from that slope. So you can see this slope is here. So you can see instability in that slope. This is gone back a few years now, 2013, but unstable conditions. So what they did is they put 12 horizontal drain holes at the toe of the slope here, and then within a couple of months the slope had stabilized and they were able to monitor the effect of that on the radar, and so they were able to instantaneously see the benefit of what they'd done, and they were able to then continue to mine down here as per the mine plan. So the monitoring and the validation and the refinement is an important part of the step. So that's it. Sorry this had to be in English, but it's better for you all, honestly. And so I'm going to hand this back over now to Eduardo. Thanks very much. I hope it was useful.
So Geoff, thank you very much for your great presentation and very clear in all the aspects of the watering and the pressurization. So if someone has any questions, this is a good time to address to Geoff. Y en español, si alguien tiene alguna pregunta sobre la presentación que ha hecho Geoff ahora, es el buen momento para realizarlas.
Silencia.
Es yeah.
Seems to be people quite shy. No seáis tímidos y aprovechar la ocasión.
Es una muy buena ocasión de tener a Geoff haciendo esta presentación por su larga experiencia. Entonces, si hay alguna pregunta sobre despresurización, drenaje, minas, sería un buen momento.
Well, Geoff, I have one, Carlos. So I've seen what you mean, this dealing with water, which is mainly a troublemaker in all the operations. Do you consider to study the geometry of the bodies always by studying the geophysical properties such as porosity and having a clear view on 3 dimensions in order to establish the numerical models?
So it's important that you start off with the geological model, and particularly the structural geological model. That's the building block of the hydrogeological model. It's also the building block of the geotechnical model. So having a clear geology is the most important step in the process. If the geology is uncertain, then it's always preferable to drill more holes to improve the geology. Geophysics, you can add on to the geology, but again, the geophysics needs to be calibrated and needs to be constrained by drill holes. So with geophysics, you're measuring the physical properties of a formation. You're not measuring the formation itself, you're measuring physical properties. And so in order for that geophysics to work, you have to have those geophysical signals correlated with the geology so you can calibrate the results. So the most important thing is geology and drill holes, and certainly you can improve that with geophysics, but there's no substitute for drilling holes.
Thank you very much.
And Geoff, I don't know if you have sorry, go ahead.
No, sir, you go ahead.
No, please, your first time from Pete also. So I have enough time to discuss with Geoff other things, so please go ahead.
Okay, so Geoff, you did mention that in a hard rock environment, the shallow groundwater influences the slope stability quite a bit.
Yeah.
And apparently, so I was wondering what means there are to study to understand the properties of the blasting affected zone, the thickness, the hydraulic conductivity, storages, and etc. Or how do we handle it in our either numerical model or in terms of representation, in terms of later on designing the drainage system or the watering system?
So that is a really good question, and there is no answer to it at the moment. So it's something that the LLP group is working on in terms of both geotechnical and hydrogeological characterization of the overbreak zone and the blast damage zone. So I just reviewed last week some of the latest research work by the LLP, so they're moving forward with that. But essentially, that is, I think the mining industry has come to the realization that that is very, very important, and it's something that we don't understand. So what I try and do and what I've been encouraging more and more mines to do is put in shallow piezometers, and I think for a large pit, so many pits I'm working on now, I've encouraged them to put in like 50-meter deep piezometers with sensors at like 50, 40, 30, 20, and 10 meters. So we have a range of sensors through the overbreak zone, so we can actually measure the response to rainfall or to surface water or to other leakage. But I think give it 2 more years and we'll have procedures in place to be able to characterize that. But at the moment, the way to do it is to put in shallow piezometers and to use the piezometer data to assume a shallow phreatic surface and to put that shallow phreatic surface into the geotechnical analysis. It's not something at the moment that is conducive to hydrogeological models because it's uncertain. So the procedure at the moment is shallow observations, assumptions, in-pit piezometers, and judgment. So that is a really good question, and that's, I think, in terms of the geotechnical community in mining, that is the biggest factor we've got at the moment. So I answered your question, but I didn't give you an answer. That is the status of the industry at the moment.
Thank you, Geoff. And well, within the same context, I would like to ask if you think that it would be viable or useful to do, for example, a packet testing in horizontal boreholes drilled into slopes to understand the hydraulic properties of that zone and its thickness, or do you think it's not worthy because it's too heterogeneous for any other reasons?
So it's probably worth trying that. There's a number of operations that have done that packet testing through the overbreak zone, and it typically tells you what you probably already know, in that the permeability in the blast damage zone is 3 or 4 times higher than the non-blast damage zone. If you have enough holes, it can give you an idea of the thickness of the damage zone. But I think what's as important is where you have structures. So the flow in the blast damage zone will be interrupted where you have structures which might bring the water to the surface, or layers of clay which might bring the water to the surface. And so I think, yep, you can try doing packet testing horizontal drains, but also you should have a close look at the geology and a close mapping of the face, where the seepage faces are. And I think that is equally important as trying to take measurements in horizontal drains. But it's something that several operators have done, and yeah, I would encourage you to do it as much as anything else to get you thinking about it.
Thank you.
I have two questions regarding modeling and analysis of slopes having to do with the effect of pore water pressure. And the first one is the application of the effective stress law. Have you encountered any slopes or open pit mines where it was decided that total stress analysis should be used because the rock is perhaps too tight and low porosity? And the second question is having to do with the coupling of hydraulic analysis and mechanical analysis. Have you encountered any situations where it was necessary or significantly beneficial to do a coupled hydromechanical analysis of the slope? Thank you.
So the question is, yes, there are a few instances where we've used a total stress approach because of the undrained nature of the rock. Again, it's quite rare in an open pit setting. It's more common, for instance, when you're analyzing a tailings embankment that you can use that approach. But where you can prove that the total stress is the effective stress component is very small, then yes, you can do it. But you should rely on actual data and actual physical measurements and actual piezometer data to establish that. And in terms of hydromechanical coupling, yes, again, it's something that is talked about a lot. But again, in Chile, many of the mines, you see the effect of hydromechanical coupling. Ambris, for instance, or Chuquicamata has a great data set, as Radomir Tomic, as does Minister Alice. They've all got very good data to demonstrate hydromechanical coupling. And where they have the data, they can use a coupled response. But I think it depends on a situation by situation basis. If you know you've got a low permeability material, if you know you've got a strongly clay altered fault, you can do a coupled analysis. But if you do a coupled analysis, it's important you get the piezometer data to validate that analysis. And there's a number of projects I'm working on in Chile where they've done coupled analysis, and then they have subsequently gone and put piezometers in to validate that. Does that answer your question?
Yes, that was very helpful. Thank you.
So it's more common. There's more examples of hydromechanical coupling in Chile than probably anywhere else. And in Spain, of course, the one that's very well documented is the marls at Cabre Las Cruces.
Just a quick question. If you have come across any wells which would drain to aquifers, just like in one of the schemes you've shown, when you have an, say, alluvial sand aquifer at the top, and then an aquitard underneath that, and then there is a, say, intermediate or highly conductive aquifer, let's say carbonate or dolomite aquifer. And have you come across, or would you suggest, say, using a single dewatering well to drain both, like having a certain filter type at the top aquifer and then another set filter set up or design at the bottom? Or or do you think it's best to separate two and have separate wells for the upper aquifer and separate wells for the lower one? Thank you.
Yeah, that's another good question. So obviously it's site specific, but as a global rule, it's better to have two different wells for a number of reasons. One is that upper alluvium or weather material has higher drainable porosity than the rock underneath. Typical drainable porosity for an alluvium may be like 15%, or for a weathered zone maybe 5%. But for a crystalline rock, even a limestone, maybe 1% or less. So there's always more water in the near surface zone, so it pays to try and tap that water with shallow wells near surface. So have dedicated wells to deal with the higher volume shallow water. The other consideration, which again is something that we've seen a lot, is that if you do screen both intervals in a well and the well is not pumping, then typically the water will flow down the well and recharge the lower aquifer. So you've always got to think about, if you do screen both, what happens if you lose the well, or what happens if the pump goes down. So there's a number of factors which make it more usual to have different wells, but in some particular settings, depending on the nature of what you're trying to do, then you can do it with one, but as a general rule, you should separate it.
Thank you.
Geoff, there is a question from Gemma Black that said, what would you say is the most challenging project you've worked on in mine, dewatering, depressurization, and why?
Oh, there's a few. So there's one in Nevada I'm working on at the moment, which is the most difficult because it is the slopes are very sensitive to water, which means we've got to have very closely spaced infrastructure inside the pit, and the slopes also deform a lot, and so we have to protect that structure from deformation. So that particular project has got a number of facets. It's got high volume alluvium, but it's also got very weak materials, very susceptible to water. So the combination of those two facets is makes it extremely difficult. So there's a number of projects like that where you have high volumes and weak materials, which is always a difficult combination. But there's a few projects I worked on like that that have been a challenge.
Oh, great. Thanks, Geoff.
So yeah, finding a source is big.
Just a quick question on the piping. Do you think, well, apparently, or as far as I'm aware, I might be mistaken, but piping is a mechanism which is still cannot be represented by other numerical methods, both in geotechnical models, neither in hydrogeological models. Correct me if I'm wrong. So
yeah, I mean, you can put there's ways of doing it in the geotechnical analysis, but because it involves physical movement of materials, it's very difficult. And so, you know, it depends on the grain size distribution. And so if it's like if you have a filter material that'll entrap the fine grain material, then you don't get piping. So it's a complicated process. But essentially, if you have any non-cemented material and have any water pressure behind it, there is always going to be a tendency for it to for the driving pressure of the water to physically move the grades, and so to lead to piping. It's something, you know, obviously sand ingress into production wells is obviously a form of piping, and there's many wells where you have local ground collapse around the well because material is piped into the well. But I don't know of any. I know of people who've tried it geomechanically, but again, the results can be quite questionable.
Thank you. So following this question, can we consider, or can we assume, or can we keep in mind, let's say that if say our either slide or phase geotechnical model doesn't suggest that pore pressure is influencing the slope stability, jeopardizing it, should we still keep in mind the piping possibility, that it will somehow affect the stability, or shall we exclude that as a risk?
Well, I think the thing with any geotechnical model is you've got to look at that model, and you've got to see what the failure mechanism is in that model. So if you do a geotechnical model and the failure mechanism is you know, sliding on bedding, for instance, then piping is probably not a factor for that. So there's always several different types of failure mode you can get, and so it's important that you look at the geotechnical analysis, you look at the geology, so and to make sure that analysis has captured all the potential failure mechanisms. So the answer to your question is no. Just because you have one set of geomechanical models which maybe simulate one type of failure mechanism, it doesn't mean to say that there aren't other types of failure mechanisms that may come into play. So as with hydrogeological models, the success rate of forward predictions using geotechnical models is also you know, not it also you know, it's also questionable. There's many forward geotechnical models where unless they've got the failure mechanism very well constrained, the success of those models is sometimes quite low. So it's the same with hydrogeology. If you know the conceptual model, the chances are your numerical model is better. Same with geotech. If you understand your failure mechanism, then you have more focus in your geotech analysis. But just because you have one type of failure mechanism, it doesn't mean to say that there aren't others.
Thank you.
Geoff and Carlos, I have another question related. How do you treat mine waters to achieve minimal liquid discharge or zero liquid discharge in order to recover valuable metals, or in order to treat the water you use for the problem of dust? Do you have any possibility to reinject the water on some aquifers, on some areas which may be, say, as a protective environment to avoid the contamination of these waters, please?
Yeah, there's lots of examples of reinjection to prevent the spread of drawdown and to keep aquifers saturated. There's many examples. Las Cruces in Spain is one that's local, where I think there's 48 injection wells in Las Cruces, and the goal of that was to prevent the spread of drawdown. There's been some water chemistry issues with it, but there are many mines all over the world that do either injection wells or rapid infiltration basins as a means to control the spread of drawdown and the means to control the chemistry. Lots and lots of examples. Yeah, the one that's highest profile in Spain is Cobre Las Cruces. But in Nevada, for instance, there's many of the mines do either re-injection or rapid infiltration. And in Australia, rapid infiltration or artificial recharge is also something that the mining industry uses a lot.
Thank you very much.
And Carlos, there is other project we are working now here in Spain that we try to do as what Geoff said, to try to control the downstream the mine, extracting water in avoiding contact with our body, control the watering inflows and the pressurization, and try to recharge as much as possible water to control the hydraulic balance and return the water to the groundwater system. So that's a lot of fun. Said Geoff, Cobre Las Cruces, and there is others here in Spain.
Yeah, well, thank you, Eduardo. Thank you much.
Okay, I should probably go. It's what 6:30.
Yeah.
So
go.
Thanks for the questions and thanks for your attention.
Yeah, I must say thank you very much, Geoff Beale and Eduardo, for the opportunity we have to have Pito with us today. And I hope it will be one of the first cooperation we may have and established with the Spanish Professional Association of Geologists, our colegio. And Pito, thank you very much indeed, gentlemen, for this profitable session. Thank you much.
Thank you, Carlos, and thank you, Geoff, for your good presentation. And only to announce that next week on Tuesday, we will have the other presentation by Jeremy Dowling for the underground mine, dewatering. So all of us are invited to attend, and hopefully it will be interesting for all of us.
Sorry, Geoff, prior to finish the chat we haven't, where is the picture we're having on the screen? Where is this open bin surrounded by water? Where is it?
That one's Diavik. There's a couple of them in Canada that's surrounded by water. That particular one is Diavik Diamonds in the Northwest Territories.
Thank you much. Quite curious.
And 90% of the water gets into the pit down one fault zone. If you can still see my cursor, there's a fault zone that comes up through here, which puts 90% of the water. So there's about 28,000 cubes a day goes through that fault zone into the pit or into the underground. Now, both of these pits now have got underground underneath them.
Yeah, thank you very much.
Okay, thank you all. I'm out of here.
Thank you, Geoff.
Thank you.
Thank you.
Bye.
Thank you for.
Bye.
Bye-bye.
Okay,
Bye-bye.
well, ladies and gentlemen, the session's finished.
Gracias a todos por participar.
Gracias a ti, Yolanda.
Adiós, Carlos.
Gracias, Yolanda. Gracias, Carlos.